Hello, everyone, and welcome to another episode of Frick Programming. This is another challenge episode, and for this week's challenge, we're actually going to do an active challenge. Currently, there's 1 day and 19 hours remaining on this. By the time this video comes up, it might be like 1 day and like 18 hours. But anyway, so we're going to go along with this. And so the challenge says a happy number is a number defined by the following process. Start with any positive integer and replace the number with the number of squares of its digits. Repeat this process until the number equals 1, at which point it will stay 1, or it loops endlessly in a cycle that does not include 1. A number for which this process ends in 1 is happy. Write an algorithm to determine whether or not a number is happy. And it gives you an example of 19. So 19, you'll split the digits up into those digits, which is 1 and 9. Then you'll take the summation of their squares, which is 82, and it goes through on to get 100 as a summation, and then that will give you 1 at the end. So if we want to go over this really quickly, so if we go and let's make some examples of this. So we have n equals 19. We're going to take their example for ours. So what it does is we need to create an algorithm that will, 1, split to individual digits. So we're going to have to take 19 and split it into 1 and 9. Then we're going to square the digits. So we're going to take 1 squared, 9 squared, 3. We're going to add them. So we're going to go 1 squared plus 9 squared. And then 4, we're going to bring this up here. So 4, check if equal to 1. So basically we're going to check the summation to see if it's 1. So 1 squared plus 9 squared equals 1. Check. And then we're going to send some to stage 1 again. Stage 1, if not 1. So basically this is going to go all the way back to here and repeats the process over and over and over again. So as we see with this, we have a process that is repeatable. And what we need to do, since we have a process that is repeatable, either put it in its own for loop or loop situation that either is a loop in and of itself or it calls itself. So in this way, we can do recursion, or we can do iteration. I myself am going to do a recursive sequence for this, or recursive algorithm for this. So basically what I'm going to do is for recursion, I'm going to call recurse method. And then I'm basically just going to have the recurse method call itself multiple times. Just keeps going in a cycle like that until we get the situation in which you want. Now, not every number is a happy number. Not every starting number is a happy number. Not every individual number that we get out of the starting number will be a happy number. So that means we need to quit out at certain points. Now, this really comes down to how slow is your algorithm. If your algorithm is slow, then you probably want a lower quit out number. But if your algorithm is fast, since this one is kind of fast, it really is, we have order n here to split things up and square them. This is all basically order n, so however long the digits are, that's our order n. This is order 1, so really our complexity is order n. Our space, big O notation, should also be order n, or order 1, since we're not actually using any more space. We're not creating any data structures for this. We're just using the same thing. So this could be big O(n) or O1, depending on how you want to argue it. Since we are creating some space to hold the summation of the number that we're then just going to pass in, that is technically, we are making a order n, but since we're not increasing what we're doing, it could also be order 1 time or order 1 space. So now that we're done with this, let's go to the code. Since we basically have our method already written out, we can easily just go to the code and start coding this. So I'm going to move over to the code. And so our first step, since I'm making it recursive, is call happyNumber recur. And I'm going to pass in the number that we have, which is n, and our starting count, which is 0. Since, like I said, not every number is going to be a happy number, we need to fail out at a certain point. Since this is a Boolean method, I do have to return this. The recursive method also has to be a Boolean method since it needs to return a true or false to comply with the original method. So int n is the number that we're given, and then int count is what I'm doing. And I'm just going to say if n is equivalent to 1, which indicates that it's a happy number, we need to return true. This is the case. These are breaking cases. So I get to make my breaking cases. So our breaking cases either return true or return false. If count is greater than 15, I'm going to return false. And then recursive logic. Since we're done with our breaking cases, we have a case that returns true and a case that returns false. Those are our breaking cases. Then we just have to do our recursive logic. So for our recursive logic, I'm going to say we have to create a summation. So int sum equals 0, since I'm going to have to use this later down the line. So my scope has to be outside of a while loop, which is what I'm going to create. So I'm going to say while n is greater than 0, we have to do stuff. And so I'm going to make the digit that we have. So the digit is going to be n modulus 10. This will get us the ones digit. And then n divided by 10, or n divided equals 10. This will get rid of ones digit from original number. And then we can say sum plus equals math.pow, which is take a number, take the first parameter and bring it to the power of the second parameter. So digit squared. And then I actually think that's it. That is that entire while loop, because n will divide by 10 and then it will just continue. And then we will return happyNumber recur with the sum that we have and plus count, which will increment our count to 1, or increment our count to 1 plus the current count, and then call the method. So the reason why we're returning sum is because our breaking case comes before our recursive logic. So if we just call this again, which is order 1 operation time, we're just calling a method that's order 1. We can just send in the new information that we have to the breaking case. There's no need to check the breaking case again at the end of the recursive logic. So if I run my sample tests, I'll see if I have any compilation errors or runtime errors. And it seems as though I've passed all 30 tests. So since I've passed all 30 tests, I'm just going to say I'm going to submit it. And with my submission, it says I'm correct. So this is actually how you were to solve this challenge. This is currently order n. We are going through this kind of n times. We don't know how many times we're going to go through this, but we're going to go in at least 15 times, but we're going to go down the number of digits in our original number and our numbers that would come after that. And we're going to do this 15 times. So this does have an order n operation. We're not going into multiple for loops. We're not getting order n squared. We're not really doing logarithmic runs. So we're not getting into any other types of big O notation. We're not using any data structures that have their big O for sorting and stuff like that. So this is order n with the time complexity. And for space complexity, I could argue it's order n or order 1. So that's what this solution comes out to be. Thank you all very much for watching this challenge run. I will see you guys next time. Thank you very much.